Alright, so now they want us to find the equation of the tangent line, the three tangent lines we just found, to f of x at each of the points below. Then draw the graphs of the tangent lines on the grid above where it's graphed. We already did that part. So let's just find the equation at x equals -4 right now. So let's look at what we have. We know the slope of the tangent line, and we said that was equal to 4. And we know a point of tangency, and that point of tangency was -4, 1. Okay, and if we're not sure how I get that, then what I can do is I know that we're at x equals -4, and I could substitute that back into f of x. If we can't see it on the graph, we could see it on the graph, so that's okay. But if I didn't know that, I could go and substitute it in. I'd get y equals 1, and then I know my slope because that's when I substituted -4 into the derivative, which f prime of x was -2x plus 4. So now let's use the point slope form of an equation of a line. I'm given a point and I'm given a slope, so we can now find our equation of the line. So my y1 is 1, so y minus 1 equals 4 times x minus the -4. We're going to call that x plus 4. Now, on the AP test, leave it like that as your answer. You never need to simplify it to y equals. Something we talked about over the summer in my class. They just said a lot of mistakes are made. It takes too much time. If they want the equation of the line, you're done. For right now, just because that's what we've probably done forever, let's write it as y equals in slope-intercept form. So I get 4x plus 16, add 1 to both sides, 4x plus 17. So these two are the same on the test. We're going to leave it in point slope form. Okay, so for the next one, I'm shortening it up. Slope of the tangent we found to be 0. Point of tangencies, -2, 5. So take a second to come up with the equation of the tangent line, add x equals -2, and then do the same thing for x equals -1. I'll fill them in right now. So we got y equals 5. Again, you could even leave it where you had in point slope form. Although multiply by 0 and then bring the 5 over. And for the last one, we get y equals -2x plus 2. On the test, if you get this, if they say equation of a line, leave it in point slope form. Just save the time, and again, you never know. You could distribute wrong, you bring something over, you make a little mistake. So just leave it as is. So now when you hear derivative, you're going to think slope of the tangent line, and when you hear slope of the tangent line, you're going to think derivative. We talked about that a little bit earlier, but now that's got to set in. So a couple examples that we're going to do now that we understand what the derivative of a function represents graphically. Let's practice using the limit of the difference quotient, which we have right here. And we use this to find f prime of x for each of the functions below. So again, f of x plus h, if it was f of 7, every place to an x, we substitute in 7, but we're going to substitute in x plus h. So take a few minutes to do these. I'll write them out, and we'll check and see how you did. All right, so here's what we get when we substitute into the difference quotient. Let's simplify, and once I simplify, I see I can cancel a few things out. So 2/3 x is going to cancel with -2/3 x. 3 is going to cancel with -3. So what am I left with? 2/3 h over h is the limit as h approaches 0, which if I put it in, I'm going to get a 0 in the denominator, but hey, I have a common term. H's cancel out. So now I'm left with the limit of 2/3 as h approaches 0. Direct substitution, there's nothing to substitute in. Limit of a constant is just the constant, so we get it equals 2/3. So we just found out that the derivative of that first problem is 2/3. Again, I think some of you might be coming up with, hey, wait a second, I'm starting to see a pattern here. All right, let's try that. All right, so the next one, again, every place you see an x, I'm going to substitute in the x plus h. So there's the f of x plus h minus f of x right here, all over h. So let's simplify the numerator. Whoa, it's getting big. But we see, hey, 1/2 x squared cancels out with -1/2 x squared. What else? Negative 2x cancels out with positive 2x. 3 cancels out with negative 3. So I have these three terms, xh plus 1 half h squared minus 2h. I notice that each term has an h in it, so I'm going to factor that out, which is great because then I'll be able to cancel that with the h in the denominator. These cancel out, and now I can just direct substitute in the 0, and I get x plus 1 half times 0 minus 2 is equal to x minus 2. So what did I just find out? I just found out that the slope of the tangent line at any point on my original function is x minus 2. So f prime of x equals x minus 2. Again, maybe looking at this, we can see how they get there. Now, if you look down bottom, it says, notice that f prime of x, f of x equals 2x plus 3 was different than the f prime of x for f of x equals 1 half x squared minus 2x plus 3. So how are they different, and why do you suppose this is so? So looking up here, when we did the original function was a line, hey, I got a constant function. When the original function, so degree 1 original function, the derivative degree 0. Here it's a quadratic function, so degree 2, and I'm getting a degree 1 function for my derivative, so quadratic to linear. So let's write that down on the bottom and um, see if we can come up with what we think it's going to be. All right, so what do we say? F prime of x for f of x when it was 2/3 x plus 3, which is a linear function, the derivative looked to be a constant function. But what's the derivative, or the derivative of f of x when it was a quadratic, the derivative turned out to be a linear function. So what can we conclude? It appears that the degree of f prime of x, the derivative, is 1 less than the degree of the original function.